The Sierpinski gasket, also known as the Sierpinski triangle, is a fascinating fractal structure. Begin with a large equilateral triangle as your initial shape. Let's duplicate and scale the large triangle into 3 equal smaller triangles. You should now have 3 smaller triangles inside the original large triangle. Continue this process infinitely many times. At each step, the shape is split into 3 self-similar pieces, each a half the area of the original. Relating to the classic Sierpinski gasket fractal, there is a fascinating variation called Sierpinski Relatives. Starting with a square which is divided into 4 smaller squares. One of these squares is then removed, and the process repeats on the remaining 3 squares. By carefully controlling the orientation of the squares before removing one, different fractal patterns can be generated. There are 8 possible rotational and reflectional symmetries of a square. The first identity means no transformation for each of the 3 subshapes. Rotate the red section 90 degrees counterclockwise, then we get a relative of the Sierpinski gasket. Each transformation has been labeled by a number from 1 to 8. We can apply any of these transformations to the squares in the construction above, and the 3 remaining squares will still fit together as before. Each relative is uniquely identified by a sequence of 3 digits from 1 to 8, denoting the transformations applied to the 3 squares at each stage. At each stage of the construction, one of these symmetries can be applied to each of the 3 remaining squares independently. This allows for 8 cubed or 512 total possible sequences of transformations. While there are 512 potential sequences, many produce identical-looking fractals due to symmetries and rotations. Accounting for these duplications, there are 232 distinct Sierpinski relatives. A remarkable property of all these relatives is that they remain self-similar, composed of 3 smaller copies of themselves, each scaled down by a factor of 1/2. This consistency in the scaling ratio gives every Sierpinski relative the exact same similarity dimension, approximately 1.58, as the original Sierpinski gasket. In summary, the Sierpinski relatives demonstrate how a simple recursive algorithm, repeated with small variations, can generate a diverse family of fractals with shared mathematical properties. The creativity of mathematicians continues to find new ways to twist and combine simple rules to form beautiful and complex patterns.